This is problem 2 from chapter 19. At a given instant, the body has a linear momentum and an angular momentum, shown here, computed about the mass center. Show that the angular momentum of the body computed about the instantaneous center of zero velocity can be expressed like this, where what we have here is the moment of inertia about the instantaneous axis of zero velocity, shown in the picture here, and the distance between the instantaneous center of zero velocity and the mass center is given here. And these two vectors here are perpendicular to each other. So we're going to go back to page 521. So we're trying to show this here. And we have the angular momentum about G. If we want the angular momentum about point A, shown here, we can use this equation where D is the moment arm, as shown in the picture here. So for us, rather than using point A, we're going to use the instantaneous center. So the angular momentum about the instantaneous center is equal to the moment of inertia about G times the angular velocity plus D is the moment arm for us, that's this distance here, times m times the velocity of point G. Okay, so that's what we get from this equation here, and this is what we are trying to show. So we have the angular momentum about the instantaneous center on the left-hand side. We need the moment of inertia about the instantaneous center on the right-hand side. So we're going to use the parallel axis theorem. That's on your equation sheet. That's equation 17.4. So for the moment of inertia about the new axis, that's going to be where the instantaneous center is. That's equal to the moment of inertia about G plus m times the distance between the instantaneous center and G squared. That gives us this. Okay, now we're going to solve for the moment of inertia about G, and then we can put that in here. So that's moment of inertia about the instantaneous center minus the mass times the distance squared. Okay, now take this and put it in up here. And that gives us this here. Now I'm supposed to get for this, if I distribute the omega, that would be the moment of inertia about the instantaneous center times omega minus this. Okay, so if this is true, then these two terms need to cancel out. But they do, because the velocity of the mass center is equal to omega times the distance between G and the instantaneous center. So if I replace this with omega times the distance here, then this and this cancel out, and I get the moment of inertia about the angular momentum about the instantaneous center is equal to the moment of inertia about the instantaneous center times the angular velocity, which is what I was supposed to show. So that concludes problem 2.